Hey everybody, today we're going to talk about nuclear chemistry, and as you can tell from the name, nuclear chemistry involves changes to the nucleus. Now that's a bit different from what we've been talking about because everything we've talked about to this point has been the electrons. Electrons in valence shells, electrons being shared, transferred, lost, gained. Well, here we're going to have changes to the nucleus, and you can actually have one element undergo a change and become another element due to the loss and gain of protons. And so I do got to warn you though, if you don't do enough practice problems in nuclear processes, the N and the U will become inverted, and then it will become unclear chemistry. Okay, I was done. Let's go to work. Well, hi everybody. Hi. Sorry about the weak joke. Today we're going to talk about radiochemistry or nuclear chemistry. It's part of the general chemistry curriculum, depending on which kind of general chemistry course you're taking. It could appear in Gen Chem 1 or Gen Chem 2. So if you're using an Adams first book, you're probably going to see this earlier in the year, and if you're using a conventional book, you see it in Gen Chem 2 at the very end. Nonetheless, what we're going to do is talk about radioactive particles. And so let's go back in history and talk about the Rutherford experiment. Now, you'd be like, hey, I didn't come here to learn no history. But, you know, this is always kind of the favorite sort of question for one of the instructors to put a history, the history of chemistry question on here. But here's what happened. Basically, 130 years ago, we didn't know much. And we just knew that certain kinds of substances threw off radioactive particles. And we can detect that, using something as simple as photographic film, and we could oxidize silver, reduce silver, and you'd see traces that there were something like a radioactive particle that struck it, but they really didn't know what the heck these things were. So they encased a particle in a big old lead box because lead blocks radiation for reasons we'll talk about in a little bit. And then if you leave a little hole and then maybe focus it through a couple of slits, you've got yourself a beam of radiation. So what they did is they said, well, we'll find out if it's charged or not. We'll pass it through these plates, and the plates will have charges on them. So there'll be electrically charged plates. The positive plate up there is positive, and then the other one, that one below it, is negative. And there were three outcomes. All right, so one of the outcomes is pew, 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 pew. Nothing in terms of its trajectory changed. And that would tell us that, oh, that particle's neutral. It's electrically neutral. The other thing that happened was that, there was this other set of particles that had their path deflected. Now, what does that tell us? That tells us that because it kind of, that tangentially sort of went towards the negative, it tells us that, oh, that thing was positively charged. And then there was another set of particles that went towards the positive charge, and then that would be something that would be negative. Now, what we did, and I mean we as in humanity, we didn't quite know what these particles were. We just knew that we called the ones that were positive, we called that alpha, and the ones that were negative we called beta, and the other ones we called gamma. And we'll talk about what each of these things are in just a jiffy here. But you can also tell one thing. Okay, yeah, we can tell that beta was negative and alpha was positive. But because beta's path was deflected in a much greater fashion, that tells us that beta was much lighter than alpha, all right? And, of course, we don't know anything about the mass of gamma because it was electrically neutral. Now, I'll just kind of cut to the chase here. We have these three particles, alpha, beta, gamma, and we're going to talk about what is their symbol, and I'm just going to cough up the details of, like, what is their charge, okay? So alpha, by the way, you can use that as a symbol, or, frankly, you can use this because, now don't think too hard, but this is just it turns out that an alpha particle is actually a helium nucleus. And a helium nucleus is just especially stable. And it happens to be that when atoms want to lose weight because they're unstable, they will fling off alpha particles. So the proper way to write this is we put the mass number on top, and that's a 4. And for both, well, no matter, it doesn't matter what symbol you use. As a matter of fact, the next example, I'll show you a little bit of both. And then, of course, the atomic number of helium is 2. All right, and so we would say this has a charge of positive 2. So that's why they were deflected up above towards the negative electrode there. And then the mass would be 4 AMUs. All right, so the next particle would be, you could use the symbol. You could use the beta symbol, or we could use the electron symbol, because a beta particle is actually kind of like a electron that came from the nucleus, okay? So then electrons are 0, roughly 0. Of course they have mass, but we kind of round it down and say it's got negligible mass. And then a atomic number of -1. So this has got a charge of -1. Its mass is squiggly equal sign, nothing, okay? Very, very light particle. And then a gamma, we don't have any other symbol but the gamma symbol, because it is actually a photon. It's a high energy photon, and it happens to be that when atoms want to lose energy, they do it in the form of a gamma particle, but it's electrically neutral and it has no mass, or question mark with regard to mass. So those are the 3 big ones, alpha, beta, gamma, which, by the way, in the Greek alphabet, that means A, B, and C. So literally, they said, we'll call it particle A, particle B, and particle C. And we don't really know what they are, but we'll just call them that. Now we know these things, that an alpha is a helium nucleus, and a beta is like an electron that came from the nucleus, and then a gamma is a high energy photon. There's also these kind of oddball things. You got positrons are actually like an electron that is positive. So it's got a charge of +1 and a mass of roughly 0. And then you got what we all know, a neutron, symbol would be N. That's got a mass of 1 and a charge of 0. Whoops, that was supposed to be a 0. So charge of nothing, but a mass of 1 AMU. Okie doke? And so there you go. Those are all the particles that you might not, okay, they're not all the particles, but the lion's share of what you might see would be those particles. And then if you know their mass number and their charge number, you can take a reaction and you can balance it. All right, so that's where we're at in life right now. What I'd like to talk about next is how do you know what each can go through? So let's take the 3 particles, an alpha, beta, gamma, and let's pretend we shot them through stuff and saw what would happen to block it. So let's first take a piece of paper, okay? And let's take an alpha. An alpha particle, and I tried to draw it here with the particles. Here's your 2 protons and your 2 neutrons. They're pretty much going to get stopped by a piece of paper. Does that make them not dangerous? No. I mean, not necessarily. I mean, if you had an alpha particle and it wouldn't go through you. But if you breathe them in, that ain't good. And that's why radon is not good, because radon is radioactive and an alpha emitter. But if you breathe it into your lungs, it could be quite dangerous. So beta particle, pew, 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 go right through paper. But, a pretty decent thickness of aluminum would stop it. And it happens to be that, it wouldn't go through that and therefore wouldn't get to the big old hunk of lead. Gamma particle, no, I said particle. Gamma is a photon, so you make the little wavy thing. This is a photon, very, very low, small wavelength. And you would need quite a bit of thickness of lead in order to stop a gamma particle. And don't get me started on gamma particles, very important part in history with Bruce Banner and the Incredible Hulk. Sorry about that. But nonetheless, you'd need like quite a bit of thickness of lead. I'd say several inches of lead. And as you know, when you used to go to the dentist, when you do go to the dentist and they give you x-rays, x-rays are lower in energy than gamma particles, and they put a lead vest on you to protect you from the x-rays. So basically, long story short, the penetrating ability of a radioactive particle is inversely related to that particle's mass. So the smaller it is, the more it's going to go through something. And that's why alpha doesn't really take much to stop it, and beta is kind of in the middle, and gamma will go through a whole bunch of stuff. All right. So that's it for the qualitative aspects of the particles. Let's talk about what happens in various modes of why does an atom just shoot off particles, right? Well, that's where we get into this. Types of decay. And so we've got what we call emission. Emission, by the way, means, and you probably know from talking about atoms and light emission, means to give off. So here we have alpha emission. And sometimes they call it alpha decay. Decay is when a more complex particle breaks down to make something simpler. Now look, gang, this is a little bit different because now instead of just balancing mass, you've got to balance the atomic numbers too. So we say, oh geez, what's polonium going to make if it throws off an alpha particle? By the way, I just repeated it to show you that these symbols are interchangeable. So the first thing you do is grab one of these bad boys, right? And we're going to go look and say, hey, polonium, that's atomic number 84. Now, sometimes a textbook problem, a homework problem, whatever, a test problem, will be very generous with you and say, okay, look, we'll give you the atomic number. But you know what? If you're just given a symbol, you're going to have to go hunt up the atomic number. Okay, cool. So then we'd say, well, what the heck is this particle here? Well, I know something. I know that if it had on the left a mass number of 210, whatever we produce on the right had to have a mass number of 210, and so that would have a mass number of 206. And then we do the same thing with the atomic number. So on the left side of the arrow, the atomic number was 84, and on the right we need to have it be 84, and that mystery particle would be something with atomic number 82, and that would be lead. So we would just write in there lead. That's the symbol of the particle that was produced when polonium-210 undergoes alpha emission. So let's do another one. Let's go down to beta emission here. Iodine-131 is what they'll give you, actually. Radioactive particles can kill cancer cells, and if you have thyroid cancer, they'll give you radioactive iodine-131. You'll be radioactive for about a week, but it'll all concentrate in your thyroid because it's iodine, and it'll wipe out the thyroid cancer. So nonetheless, that's a beta emitter. Beta emitter is a little bit more nasty on cancer cells and everything. But what I'm going to do now is same process, gang. Now watch out, the negative sign can kind of get people. But iodine, atomic number 53, let's write that in. And then, of course, the atomic number on the right would have to be whatever blank plus -1 to make 53 is, or 54. And if we take a quick look, when iodine-131 decays, it would produce xenon. And then the mass number would be 131. And you know what I tell people to do? I tell my students, like, look, if this kind of thing's going to mess you up, go ahead and just circle, each side. Say, okay. Darn. My memory card ran out. And I just kept talking, and I looked up, and it told me. So what I was going on, I was really on a roll there, guys. I was saying, look, you can circle each and just say, hey, all right, is the mass number 131 on both sides of the arrow? And you can actually get 131, 0 plus 131, check. 53, -1 plus 54, check. A lot of times I'll see students write a 54 there, or excuse me, I see a 52 there, but that's because they're trying to add -1 to 52 and get 53, okay? So don't do that. Gamma emission's kind of weird, gang. Basically, we're saying that a high energy atom, like cobalt, it's just got a discharge energy. So we use this little asterisk to say, okay, high energy cobalt particle will make lower energy cobalt plus a gamma. And so we kind of just lump it in here with this kind of balancing because we're in the neighborhood. You know what I'm saying? So don't get too stressed out about gamma. It's real easy. You just get the same thing on the left and right. It's just a different energy particle. There are some others that pop up. So there's emission and then there's capture. Look, gang, the stuff balances the same way. Make the mass numbers and atomic numbers equal on both sides. So electron capture, first let's go look up what the atomic number of potassium is. It's 19 if you recall. And so, okay, potassium 40 is going to, instead of actually emit, you can actually shoot electrons into things and the nucleus can rearrange and you can kind of synthesize other elements that way. And so the bottom line is, same concept. I'm going to get something of atomic number 18. It's going to have a mass number of 40, and it's going to be argon. All right. Now, in a future video, we'll talk about why this stuff happens. But right now, we're not focusing on that too much. Positron emission. So atomic number 8 is what oxygen is. I'm making us remember here that a positron is mass number 0 and atomic number +1. So positrons are kind of weird, and I don't want to get into it about a positron plus a neutron is what a proton is. And so then what we're going to do is we're going to just keep going and do the same thing. We're going to end up getting 7, 15. And then if you look at your periodic table, that, my friends, is a nitrogen, is what will be produced from that process. Cool? All right, well look, just so everything doesn't become unclear, let's practice. Let's do some practice and then we'll let you go here. So, okay, let's play fill in the blank of what the particle's going to be. So what we got going on here is we've got a carbon 14, and then goes to make a nitrogen 14. And so what's the mystery particle going to be? Well, it's going to have a mass number of -1 to make 6 on both sides, and 0. That, my friends, is a beta particle. And carbon 14 is a beta emitter, and that is how they actually can, based on the number or the amount of decay, they can actually date things due to the half-life being like 5,730 years. We'll talk about that in a future video, okay? Here's something tricky, like what the heck's going on over here, right? Well, and then watch out, coefficient. If you really want to watch out for the coefficient, what you could do is do that, and you'd have to multiply. But if you really want to, like I do, protect myself from myself, you could just write it twice, and you could see, oh, that's 8, and then that's a 7. And so whatever this is got to have a mass number of 1, and then of course lithium is atomic number 3. You know, we're just go, hug one of these things and find lithium. And then, therefore, 2 plus 2 is 4. The mass number on both sides of the arrow has to be 4, which means that has to be a 1. You look at it like, what the heck has a mass number of 1 and atomic number of 1, and that's a proton. Now you can use a P. Usually they use the hydrogen for that symbol, and it's a proton. So see, it's really not all that hard. Just takes reps, gang. Just get the reps in. Here's one that looks intimidating, and as a matter of fact, this is going to be an example of, we'll talk about it in a future video, nuclear fission, big particle becoming smaller particle. And you're like, what the heck is Cm? I don't have names on this periodic table, but that is curium, named after a famous madam. All right, and that would be atomic number 96. Now, strontium, atomic number 38. Okay, so strontium right there. And so we'll go ahead and write that in. We've got 4 neutrons as a result. And so we've got to make sure that, I guess what I would do the easy part first, which would be the mass number. And so we go, I know I'm using a calculator. I know, it's crippling self-doubt is making me grab my calculator and know that it was 58. Atomic number 58, what's that? That is cerium. Curium makes cerium. Are you serious? Yeah. And then what we've got going on is 98 plus 4 times 1. All right, 4, multiply through that coefficient. 98 plus 4, 102 minus 250. I'm not even going to reach for my calculator. I'm feeling that confident. Cerium 148. And there you go, gang. That's all there is. It really, honestly, just takes a little bit of practice. And so I think you've got this. So now, what we did not discuss is why any of these things do this. Why does something undergo alpha emission? Why does something undergo beta emission? It's all about 2 different trends of nuclear particles being how many neutrons and protons there are. We'll talk about that some other time. I think you've had enough. All right? Okay, gang. Catch you later. Be nice to each other, and we'll see you in the next one. Ta!